So in previous lecture, we have discussed the single stack variable reluctance stepper motor in detail with its construction and working. Now in this particular lecture, we are going to discuss the mode of excitation of a single stack variable reluctance stepper motor. And if time permits, we will discuss a construction of a multi-stack DC stepper motor. Okay. So let's start with the mode of operation or mode of excitation of a single stack stepper motor. So whatever stepper motor which we have considered in previous lecture, which is a single stack type, that motor is 4 pole, 8 pole, 4 phases, 8 pole single stack variable reluctance stepper motor. So that consists total 8 poles on stator winding, and that 8 poles have been excited, or that 8 poles have been covered with a concentric coils, and that coils are connected in such a way that there will be formation of a 4 phases. So that 4 phases are phase A, phase B, phase C, and phase D, and basically the opposite poles consist a same phase coil. Okay. Now to excite that particular 4 phases, we use a semiconductor switches, and as per the predetermined sequence or as per the requirement of a step angle, we generally switch that particular switches in on condition and off condition. So there is a certain switching sequence, and according to that switching sequence, we obtain the rotation of that particular rotor in certain step. So whatever rotor which we have considered, that rotor is the salient pole rotor with 6 teeth on its rotor periphery. So there are total 6 teeth on rotor periphery, and according to the switching sequence, now we have seen the first operation with a single mode switching. That means when we switch one switch at a one time, that means say when S1 is in close position, the motor is at that is pole 1 and pole 4, that two rotor teeth align with phase A, and that we consider as a initial state of that motor. Then when we switch S2 by switching off S1, under that particular case, pole 2 and pole 5 align with B and B dash, because B phase get energized, A phase get de-energized, and under that case, motor will rotates in a first step of a 15-degree in counterclockwise manner. Same operation, same 15-degree revolution in counterclockwise manner can be obtained by following the switching sequence as S1, S2, S3, S4, again S1, S2, S3, S4, and so on. If we have to reverse the direction of that motor, say we have to run that motor under a clockwise direction, then we have to reverse the switching sequence. That means initially if S1 is close position and if motor is rest at its initial position with 1,4 aligned with A dash, then we have to turn on switch S4. So under this case, motor will runs in counterclockwise direction, in clockwise direction with a 15-degree, because when we close switch 4, the coil D dash get energized and coil A dash get de-energized. So if coil D and D dash get energized, the rotor teeth 3 and 6 are trying to align under the coil D dash, and that will rotates that rotor in clockwise direction by step of 15-degree. So we can achieve this clockwise stepwise rotation by following sequence S1, S4, S3, S2, S1, and so on. That means simply we have to reverse the switching sequence. So why that motor rotates at a 15-degree during each switching operation? So that 15-degree is actually the step angle for that motor, and we determine that step angle for stepper motor by theta s is equal to 360 divided by m multiplied by nr, where m is the total number of stator phases and nr is the total number of rotor teeth. So for this present case, m is equal to 4 and nr is equal to 6, therefore theta s is equal to 15-degree. So with this single mode switching excitation, we either run that motor in clockwise direction or in anti-clockwise direction or counterclockwise direction by a step of 15-degree during each switching condition. Okay, so either we run that motor in counterclockwise direction with a 15-degree, or we run that motor in clockwise direction with 15-degree. Now, whether same motor can be used to uh, attain some another step angles, maybe with half step angle or full step angle with some different positions. So yes, we can use this same motor for another step angle or another positions. Let's say if you have to run that motor with a 7.5-degree first, and then we have to switch that motor by 15-degree, that means with full step angle, then that is also possible with a two switch switching or two-way excitation. Or there may be another form we can obtain the 7.5-degree step angle, that means 7.5-degree movement of that rotor in either clockwise or counterclockwise direction by achieving 2-1-2-1 switching sequence. Okay, so that are the different mode of excitation for stepper motor, according to which we can change the position of that same stepper motor. That means initially whatever motor operation which we have discussed in previous lecture, for that particular motor operation, we achieve 15-degree step movement. That is initially rotor is at 0-degree, and we can obtain 0 to 15-degree, then 30-degree, 45-degree, and so on. Okay, so that this 0, 15, 30, 45, 60-degree. So that operation we have learned in previous lecture. Now whether another operations are possible, so yes, that operation, that step angle, that displacement of rotor or position of rotor is also possible with some alternate switching mode. Okay, so we are going to discuss that mode of switching or modes of excitation in today's lecture. So same stepper motor can be operated in different modes depending upon the excitation sequence which is provided for stator pole or stator phases. So depending upon the excitation sequence, we can run same stepper motor for the different switching mode or for the different step positions, or you can say that rotor position. So when one phase is energized at a one time, the mode of operation is generally known as a single phase excitation mode, or that is also known as a one phase or full step on mode. Okay, which we have discussed in previous class. So either we can run that particular motor in counterclockwise or clockwise direction with a step angle of 15-degree. So that particular mode of excitation is known as a single phase or one phase or full step on mode. Now in this particular mode, the stepper motor gives the maximum step angle for which that motor is designed. Now there are some alternate modes of operations by which we can change the position of rotor with either full step angle or with half step angle. That means for said motor, we can run that motor by full step angle of 15-degree, but with some different position. Okay, so or maybe with a half step angle, that is means by 7.5-degree. So that is also possible. Okay, so how we can achieve these different step or different operations of motor by changing this mode of excitation. So we are going to discuss that part in today's lecture. Okay, so let's start with the first mode of excitation with the which is a two-phase on mode. Now to explain this particular mode, consider the stepper motor which is we have considered in previous lecture. So let's I'm going to upload that particular stepper motor on board. Okay, yeah. So I'm trying to upload that stepper motor which we have discussed in previous lecture. Yeah, so we have discussed this particular stepper motor in previous lecture, which is the four-phase 8-pole single stack variable reluctance stepper motor with a switching circuit as shown in figure 1.2. So now we consider the same motor for this two-phase on mode operation. Now with S1 in on position and S2 with S1 in on position, whatever rotor position is given, that rotor position is as shown in figure 1.3. So with S1 on, so the first case we consider with S1 on. Okay, so with S1 on, the rotor position is as shown over here. So now when we switch on S1, at that time A and A dash, that particular coil get energized, and under this particular case the rotor pole 1 and 4 tries to align with a stator poles A and A dash. Okay, so that means these rotor teeth 1 4 align with this A dash because it attains the minimum reluctance path in with by traveling with a minimum displacement. So that minimum reluctance path is when that 1 4 align with A and A dash. Okay, so under this particular case, when switch S1 is under closed condition, whatever motor is there, that motor, that means when this we close this switch S1, motor attains the position, that is rotor attains the initial position with S1 with 1 4 aligned with A dash. Now we consider say this as a 0 degree operation. Okay, now suppose the mode of excitation is two phase on mode. Now by keeping S1 under on condition, if we switch on S2, that means with S1 in on position, if S2 is also switch on, what will happen? So under this particular case, now our conventional operating mode, when we close S1, when we switch on S2, sorry, when we open S1 and when we close this S2, then under a single phase excitation mode, rotor tries to run or rotor tries to move forward, that is in counterclockwise direction by 15 degree. Now same thing will happen over here. So when during as S2 is on, the rotor tries to rotate in counterclockwise direction by 15 degree because coil B and B dash is under energized condition. So this will tries to move this rotor by angle of 15 degree in counterclockwise direction. But at the same time, coil S1, sorry, coil A dash, that coil is also in energized condition as S1 is also in on state. In single phase excitation mode, when we switch on S1, we switch off S2. That means while when S1, S2 is turned on, at that particular time, we turn off S2 so that rotor tries to rotate in counterclockwise direction by 50 degree because during this operating mode, coil B dash get energized while coil A dash get de-energized because S1 is under off condition. Okay, now here both switches are in on condition. So initially when S1 is under on condition, the rotor align with A dash. Now when we switch on or when we turn on S2, keeping S1 in on condition itself, that means under this case now this S1 is on, S2 is also on. So what will happen? As S2 is on, coil B and B dash get energized. So when this coil B and B dash get energized, rotor tries to rotate in counterclockwise direction by 15 degree, and under this case rotor pole 2 and 5 or rotor teeth 2 and 5, they are tries to locate under B dash. At the same time, S1 is also in on condition, that means the coil A and A dash, that is also in energized condition, and this particular energized condition creates the force of attraction on pole 1 4 that will attract this particular 1 4 in clockwise direction. Means effectively this 2 and coil B and B dash tries to rotate the rotor in counterclockwise direction by 15 degree. At the same time, the A and A dash coil tries to rotate this particular rotor with a force of attraction. Now these both coil carries the same current, so effectively rotor will tries to move in forward direction, that is in counterclockwise direction, by a current of by a step angle of 7.5 degree. So when two switches are under on condition, the rotor moves by 7.5 degree in CCW direction, that is in counterclockwise direction, and take a rest position as shown in figure 1.7. Why this is so? This is because both coils are under energized condition. So coil B dash tries to rotate rotor in counterclockwise direction by 15 degree. At the same time, coil A dash is also energized, which attracts rotor teeth 1 and 4 in clockwise direction, and due to the same current flowing through both coil, the equilibrium condition achieve or attains when rotor moves in forward direction or counterclockwise direction by 7.5 degree. So with this particular condition, now rotor attains the position of a 7.5 degree from its initial rest position by moving itself in counterclockwise direction. Have you understood this?
Yes, sir.
Okay. Now say this is for S1, S2. Now what is next case? Now we have to turn off S1. We have to turn off S1. So next, now open S1 and close S3. Under this particular case, S2 is under turn on condition or S2 is in on condition. Now please pay attention, this is very important. So when S1 is turn on, sorry, when S1 is turn off, let's say now second mode. Now under this particular case, now we are going to open this switch S1. So now switch 1 is in open condition. Switch 2 S2 is in closed condition. Switch 3 S3 is in closed condition. So we are going to turn on S3 by opening S1. So that is second thing. Now what will happen? So when we open S1 and we close switch S3, the poles which are corresponding to phases B and phases C, that poles get energized. So the initial position of rotor is as shown in figure 1.7. So whatever poles which are lies under B phase and C phase, that both phases or both poles get energized. Now if you look towards this particular diagram, under this particular case, both B and C phase are get energized. Therefore, rotor pole 2 and 5 tries to align itself in forward direction under B and C. Again, at the same time, rotor pole 3 and 6 also tries to align itself under influence of stator pole C and C dash, and that will achieve the 15-degree rotation in counterclockwise direction. So the equilibrium position is the 15-degree rotation after the initial state. So now rotor position, when S2 and S3 are under on position, this rotor position is at 15 degree from its initial state with S1, S2 is under on position. Okay, because both poles or both coils exert the same force in same direction, and due to that force, rotor again tries to rotate by 15 degree itself. Okay, so rotor rotates by 15 degree. So now the position is 22.5 degree in counterclockwise direction from its initial state. Now next mode of operation is, now we have to turn off S2, we keep, and turn on S4. That means open S2, close S4. Again under this particular case, the motor will rotate in forward direction, that is in CCW direction, by 15 degree. Okay, so now in this particular mode, there will be two phases excited at a time, but we obtain the rotation of a rotor by a full step angle, that is by 15 degree. So let's try to understand the truth table for this two phase on mode. So now initially only when S1 is under on condition, under that particular case, the rotor S1 on, all other switches are off. So under this particular case, the rotor is rest at initial position. We consider that for reference by 0 degree. So the position of rotor is at 0 degree. Now when we turn on S1, turn on S2, keeping S1 under on condition, that means when S1, S2 both are on, rotor moves in counterclockwise direction by 7.5 degree. Now next operating mode is, now we have to turn off S1 by turning on S3. That means S1 is open, S3 is closed. Under this particular case, rotor tries to rotate in counterclockwise direction from its initial position by 15 degree. So initial position is 7.5 degree position. in counterclockwise direction, rotor moves by 15 degree. So now from its initial position, that is from zero stationary condition, rotor is at 22.5 degree forward, that is in counterclockwise direction. Now next step is close open S2, close S4. Under this case, switch S3 and S4 both switches are in under on condition. Rotor will again rotates in counterclockwise direction by 15 degree and attains a position which is 37.5 degree in counterclockwise direction from its initial rest position. After that, open S3, close S1, open S3, close S1. So now under this case, S4 and S1 both switches are in on condition. Rotor will again tries to rotate in counterclockwise direction by 15 degree. So now this will be the new positions of rotor with a two pole excitation mode. That is 0 degree, 7.5 degree, 27.5 degree, 37.5 degree, 52.5 degree, and 67.5 degree. Only keep in mind, in two pole excitation mode, when we switch or when we turn on two switches simultaneously, or when we keep two switches under on condition at a particular instant, rotor rotates with a full step angle. Okay, but its initial position is 7.5 degree. Initial movement is only 7.5 degree, and from that 7.5 degree onwards, rotor will rotates with a full step angle of 15 degree. Okay, so this is about the two phase on mode. Now next one is second possible operating mode of rotor is 2-1-2-1 phase or half step or mode of operation. Okay, so in two phase mode of operation, a step angle is 15 degree itself. So stable position corresponds to switching operation lies between the stable position correspond to single phase on mode. Okay, so actual rotor position is in between single phase on mode. Now next mode of operation is 2-1-2-1 phase or half step mode of operation. Okay, now this is somehow interesting. So with this 2-1-2-1 switching operation, we can achieve half step. That means we can run that, or we can move that rotor in counterclockwise direction or in clockwise direction by 7.5 degree. Now in this mode also, in two phase on mode also, clockwise direction, that is reversing the direction of stepper motor is possible. Only we have to reverse the switching sequence. That means initially when S1 is on, under this case, if we have to reverse that, or if you have to run that motor in clockwise direction, rather than switching S2, turn on S4. Okay, so switching sequence under this case is, that means if you have to rotate that motor in clockwise direction, what will be the switching sequence? Initially S1 is on, next S1, S4. After that, we have to turn on, close this, open this S1, then close S3. So next is S4, S3. Then open S4, close S2. So next mode is S3, S2. After that, open S3, close S1. So next mode is S2, S1. Again, next mode is S1, S4. So in this way, we can achieve the clockwise direction of motor by full step angle of 15 degree, but with the position 0 degree, 7.5 degree, and then after 15 degree each. Okay, so that reversing the direction of rotation in two phase mode of operation is also possible. Only we have to reverse the switching sequence of all switches. Now next let's focus on 2-1-2-1 phase or half step mode of operation. Now in this particular mode of operation, we can get a step angle whose value is half of the full step angle. That means here for the considered motor, the step angle is 15 degree. Now we achieve half step rotation. That means it is possible to run motor in counterclockwise or in clockwise direction with a step of 7.5 degree. So now this mode combines one phase and two phase on mode. So this is a combination of single phase on mode or single step mode and double step mode. Okay. Now to explain this particular mode of operation, let us consider the motor as shown in figure 1.3. Okay, so let's consider that particular motor. So I'm going to erase this board and yeah, so I'm going to upload the figure which is corresponds to 1.3. Yeah. Okay. Okay. So let us consider the initially phase A is excited, rotor is at initially equilibrium position with 1 and 4 rotor teeth aligned with a phase A and A dash. Now under this particular case, the switching sequence is only switch S1 is in on condition. Switch S1 is in on condition. That means we or on, or you can say that simple close condition. Let's consider open and close. Okay, S1 is in close condition. Okay, so this is the initial position of motor under consideration for 2121 mode of operation or half step mode of operation. So we consider the switch S1 is in on position or in close position. Rotor attains position which is indicated by figure 1.3. That means rotor teeth 1 and 4, that rotor teeth are in alignment with A and A dash. Now we S1 on, S2 is also switch on. So now what is next sequence? Now with S1 on, now we have to switch on S2 or we have to close S2. Yes, so definitely under this particular mode, rotor rotates in counterclockwise direction with angle of 7.5 degrees. So this is 0 degree operation. Now with this particular case, rotor rotates in counterclockwise direction with rotor angle or with angular position of 7.5 degree. Okay, so this is as discussed in previous type or previous mode of operation. Now when we turn on S2 or when we close S2, coil B get energized. So that as both A and B get energized, the rotor tries to rotate in forward direction by 15 degree, but at the same time rotor teeth 1 and 4 get attracted towards coil A because A is under energized condition. Therefore rotor will come back by 7.5 degree. Now why this 7.5 degree or why equilibrium is at 7.5 degree location? Because both coils carries equal current, therefore that both coil will generate the equal magnetic field, and due to this the equilibrium will achieve when the position of rotor is 7.5 degree in counterclockwise direction from its initial 0 degree position. Okay, so this is now step. Now there is a certain difference or small change in switching sequence. So mode is 2121. Okay, so now at this particular moment, two switches are under closed condition. Now for next switching case, now turn off or open this switch S1. Open this switch S1. Now if we open this switch S1, S2 is in on condition. Okay, now what will happen? So under this case, when S2 is in on condition, that means when S2 is in closed condition and when S1 is open, the rotor will try to rotate in counterclockwise direction by 7.5 degree, and the pole 2 and 5 of a rotor tries to align with B and B dash. Okay, so here this is the initial position. Okay, initial position by 7.5 degree when S1 and S2 are in on condition. That means under that particular case, rotor is at 7.5 degree in forward direction. That means this particular case. Okay, now for such case, what is switching condition? Both S1 and S2 are in close position. Now the next mode of switching is now we open S1. So when we open this S1, by keeping S2 in closed condition, the coil A dash get de-energized, whereas coil B dash is under energized condition. And due to this, Now rotor teeth 2 and 5 try to locate themselves under influence of B and B dash. Therefore, they will move in forward direction by angle of 7.5 degree. So here the rotor will rotate by 7.5 degree in forward direction so that these 2 and 5 get in aligned with B and B dash. Okay. So now what will be the position, angular position from initial state? 7.5 degree in counterclockwise direction. So from initial state or initial position, rotor is now in counterclockwise direction by 15 degree. Okay. Now next switching is 2 1. So 2 complete hua, 1 complete hua. Next one is again 2. So 2, that means now we have to close switch S3 keeping S2 is under closed condition. So now close switch S3. What will happen? When we close switch S3, coil C dash get energized. As S2 is under also in closed condition, coil B is in also energized state. This will tries to rotate rotor so that coil rotor pole 3 and 6 tries to align under C dash by 15 degree, but at the same time the rotor will rotate or rotor will attracted towards B dash in clockwise direction by 7.5 degree. So effectively rotor will rotates by 7.5 degree in counterclockwise direction. So here the rotor will attains a new position in counterclockwise direction by 7.5 degree. Okay, so what will be the next position? Next position is 22.5 degree in counterclockwise direction from its initial state. After that, next one is 1. So for this one, now we have to open switch S2, keeping S3 in closed condition. So open switch S2, S3 is under closed condition. What will happen? So when S2 get opens, coil B dash get de-energized. As S3 is under closed condition, coil C dash is under energized state itself. So rotor will tries to move in counterclockwise direction so that teeth 3 and 6 are in alignment of C dash, and that will achieve 7.5 degree forward motion with angle of 30 degree. So if I consider or if I say truth table of this half step mode of operation, this will be the truth table. So what will be the switching sequence? So I will give you that switching sequence. Initially S1 is on, after that 2, that means S1 S2, after that 1, so we have to open S1, so S2 is under closed condition, then again 2, so we have to close S3 by keeping S2 is under closed condition, then 1, so open this S2, so only S3 is under closed condition, then once again 2, so for this purpose we have to close S4, S3 is initially in closed condition, next open S3, S4 is under closed condition, after that S4 and S1. And then this particular switching sequence will continue so that rotor will rotates in counterclockwise direction by a step angle of 7.5 degree. If we have to rotate the rotor in clockwise direction, this is I am talking for CCW rotation, that is counterclockwise direction. If you have to move rotor in clockwise direction, okay, clockwise direction, then we have to reverse this particular sequence. So under this case, initially S1 is on, now 2 switches on, so we have to on S4. So S1, S4. Then we have to open this S1 so that S4 is under on condition. Then by keeping S4 on, close S3. That means both S4 and S3 are under closed condition. Then open S4 so that S3 is only in closed condition. Then keep S3 in closed condition, close S2. Again, next open S3, keep S2 in closed condition. Next, keeping S2 in closed condition, close S1. Next, close open S2, keep S1 in on condition and follow same switching sequence so that rotor will rotates in clockwise direction by angle of a 7.5 degree. Okay, so in this way we can achieve half step movement of a rotor in either clockwise direction or in counterclockwise direction by using 2-1-2-1 switching mode, which is also known as a half step mode of excitation or half step mode of operation. Have you understood this? Yes. Have you understood?
Yes, sir.
Okay. Yeah. Yes. So now this two-phase on mode operation has advantages over the single-phase on mode because it reduces the oscillations in the rotor positions. Uh, so if the rotor rotates with full steps, under this particular case, there may be chances of oscillation, but this oscillation can be reduced. Again, the smaller, or you can say that half step movement of rotor is also possible using two-phase on mode. Okay. So in two-phase on mode, the two conducting phases forms a closed loop for the current generation by EMF induced in the oscillation of a rotor. Okay, so there is a formation of closed loop in two phases itself. Okay, so that for that purpose, if I consider the initial diagram, this. Okay, so here when two phases are under closed condition, two switches are under closed condition, there is a closed loop formation, and this closed loop formation circulates the current which induces the EMF, and that EMF generally produce the damping itself, damping against oscillation. Okay, so that will reduce the oscillation in rotor. So that is about the two phase on mode. Okay. Now next one is the multi-stack mode, multi-stack variable reluctance stepper motor. Actually operation is similar to single stack variable reluctance stepper motor. Only there is a difference in construction. There is a slight change in construction. So now what is constructional difference? The multi-stack variable stepper motor is generally used for high torque because it has high torque to volume ratio and it has more efficiency as compared to single stack stepper motor. So now in this particular type of stepper motor, each phase has a separate stator and a rotor, which is known as a stack, and that are connected. Okay, so every phase has separate rotor and stator. So that particular combination is known as stack. Now the stator stack generally consists a salient pole wire winding. That means winding is a salient pole winding. All the coils in stator stacks are connected in series, and all poles facing the rotor becomes either north pole or south pole when that coil is excited. So when we excite a particular rotor stack coil of particular phase, on its corresponding rotor stack, either north pole or south pole will create it. So if you look towards this longitudinal view of multi-stack stepper motor, then there are different or a pair of stator stack and rotor stack for each phase. So when we consider phase A and phase A, then this is A dash. So for phase A, there is a separate rotor stack. For phase B dash, there is a separate rotor stack. For phase C dash, there is a separate rotor stack. So if we see that particular motor constructionally, then how that motor looks like. So if we study cross-sectional view of these multi-stack motor, then yeah. So this is the cross-sectional view of a multi-stack motor. So here, as I have told, on same shaft, there are rotor stack, different rotor stacks. Okay, so if you look towards this shaft, there are total 3 rotor stacks because motor is a 3-phase stepper motor. Okay, or that motor consists 3 phases, 6 poles on stator. So 3 phases, phase A, phase B, phase C. For phase A, there is a separate rotor stack. For phase B, there is a separate rotor stack. For phase C, there is a separate rotor stack. Now, in between adjacent rotor stack, there is a angle of a 15 degree. That is displacement of a 15 degree. So, phase A and phase B, the rotor stack for phase A and phase B, that particular rotor stack have displacement of 15 degree, means the rotor tips of stack A is displaced by 15 degree from stack B. Rotor tips of stack B are displaced by 15 degree from stack C. Okay, and rotor tips of A and C has phase displacement of 30 degree. Okay, so that is actually difference between single stack and multi-stack motor. So especially these motors are used for high speed, high torque operation. So multi-stack motors have larger efficiency when we use that particular motor for high torque application. So actually in your syllabus, multi-stack motor, that part is not there. Okay, only single stack variable reluctance motor is there. Only for extra understanding, I have shown that construction. I'm not going to explain that part detail. So I will share this PDF on your WhatsApp group, on your Google Classroom. So refer that PDF to understand the concept of multi-stack stepper motor. I will upload some animated videos of multi-stack stepper motor on Google Classroom. So you can refer that videos also for better understanding about the working of a multi-stack stepper motor. So only keep in mind, multi-stack stepper motor consists the separate pair of a rotor stack and stator for each phase. So phase A has its own rotor stack, phase B has its own rotor stack, and so on. So every phase has its own rotor stack, and two adjacent phase rotor stacks have been displaced by 15 degree displacement. That means the rotor teeth of phase A displaced by 15 degree from rotor teeth of phase B, and so on. Okay. So here we have completed variable reluctance stepper motor. So in next lecture we will discuss the permanent magnet stepper motor and hybrid stepper motor. Okay. So which are remaining two types of stepper motor. So we will discuss that particular two types in next lecture, that is on Monday.